This is an example of a second-order transients problem in Circuit Tutor at level 1, and we're going to select problem type 2, which is a parallel LC circuit. So as always, it's a good idea to view the introductory tutorial, which is very important for this particular game. And also you may wish to view examples, and just to show you there is a special interface for doing that in this case, where you can select whether you want to see the entire thing, which is pretty much the default, or whether you can choose only to see the work at certain particular times. Then you can also choose how much simplification to show at each of these different calculations, whether you want all the simplification or just no simplification. And likewise for the simplified matrix equations, you have the option to show those or not to show them for each step, or just overall where they apply. Okay, so I'm going to skip that for now, and let's jump into a problem here. Okay, so here's an example of a second order problem. Notice that the inductor and the capacitor in this case are in parallel, and the sought voltage, or the sought quantity rather, is the capacitor voltage, which is different than the other problem type where they're in series. Okay, as always, you have the option to give up at any time and see a complete work solution for no penalty. You can also get written or video help. So let's begin. This type of calculation requires 5 different types of calculation at different moments in time, starting at 0 minus, just before the switch is thrown, 0 plus just afterwards. Then we're going to have to do the first derivative circuit right after opening the switch. We're going to have to find our Thevenin seen from the terminals of the parallel inductor and capacitor, and finally the sought value of the capacitor voltage at infinity. So let's get started with, and generally we want to go in chronological order here from left to right. So start at 0 minus. And the first step here is always to, as similar to the first order transients problems, is to reconfigure the circuit for analysis at this particular time. So it's already changed the labeling for you to reflect that t equals 0 minus, which is important. And now we're going to do the rest by reconfiguring the circuit. So we go into the circuit editor in reconfiguration mode. There's the instructions, which we don't need right now. And the first thing we'll always want to do in reconfiguring the circuit basically is to set it up for analysis at this particular instant in time. Remember that at t equals 0 minus, because that switch has been closed for a long time before being opened at t equals 0, that the circuit will come to steady state, and we have to take that into account. Now, we also wanted to change the switches in this case, so because at 0 minus that switch is not yet opened, so it's going to be equivalent to a short circuit. So here I will change this to a short circuit. If it was the other type of switch, then of course it would be an open circuit, in which case I would just delete it. So that's the correct step there. And the next thing is, for the capacitor and the inductor, in second order problems, it's always necessary to find both the inductor current and the capacitor voltage at 0 minus. That isn't necessary for both of those in first order problems, but it is in second order problems, because these are the only 2 variables that will be preserved after the switch has acted. So since there isn't already a sought current on the inductor, we're going to have to add one there. This is an essential step. So we're going to add a sought current. In this case, I want to try to maintain sort of a passive sign convention with respect to the existing capacitor voltage. So I'm going to put it going from right to left there, and that way it points into what's the positive side for the capacitor voltage. Just makes that a little bit more convenient. And now we also have to change the inductor and the capacitor to their steady state equivalents. And remember that just as in first order problems, an inductor in steady state, because V equals LdI dt, has basically no voltage, which means it's equivalent to a short circuit. After all, it's just a coil of wire. And a capacitor in steady state, because I equals C dV dt, has 0 current, and therefore it's the dual of the inductor, so this is going to be an open circuit. Now I can't just delete it here, because that would leave no place to put this sought voltage label, so I have to change it into terminals, which are allowed to have, there's basically a place to put that sought voltage there. Okay, so we've changed those to the appropriate steady state situations, and we created all the SOT variables that we will need. So we're done reconfiguring the circuit. But again, do remember that you need both of those SOT variables at 0 minus. That's important, and it'll give you an error if you don't do that. Okay, so now we have to evaluate these two quantities. You see the capacitor voltage is going to be trivial because it's in fact shorted by the inductor, and therefore that's easy. But the inductor current, well, that's actually going to be pretty trivial here, but let's go into the circuit editor just to emphasize that. And again, we get some instructions there. And a key feature here that it will really help you to notice, instead of doing a full-blown mesh analysis or something like that, is that there's a wire going all the way across the circuit, cutting it basically in half. And as you may remember, that means that the circuit is in fact hinged. In other words, if I remove this node here and all its associated things, that's basically going to split the circuit in two. And so what happens over here is not going to affect what happens over here. You really can't feel it at all. It's the same as being connected, the two halves being connected by a single wire. In fact, we could redraw it that way, although I'm not going to, and the circuit editor won't really allow me to do that. But in any case, what that means basically is that these elements, since they have no bearing on their SOT variables, can simply be deleted. So I'm going to just press the delete key here to get rid of that, and do the same thing with the 1 ohm. And it says I correctly deleted a set of elements that was removably hinged with respect to the rest of the circuit. Okay, that's all I guess I could remove this resistor since it's shorted. I may as well do that too. And it's shorted by the inductor basically. And now we're done. And obviously we have no sources in this circuit now, and there's no path for current to exist. And so the results will be quite trivial. So we're just going to select a single loop or no loop option here. And do our SOT capacitor voltage. And as we see, that's equal to 0 because it's shorted. So that's very easy. Don't need any fancy analysis there. And likewise, for the SOT branch current, that's equally easy here because this capacitor basically is an open circuit, so everything is dangling. And also, there's just nothing to drive the current. So once again, we just say that this is equal to 0. You cannot put a 0 in this term, so you have to use the 0 term. Okay, so that's all done. And now we can say no more equations there. And we've completed the analysis at 0 minus successfully. So now next step would be to go to 0 plus. And so we'll just click on that button, and once again it asks us to reconfigure, and it's already changed the labeling for us to indicate the time 0 plus, which would be important to remember to do if you're doing this on paper, because it's not VC of t or IL of t. It's only valid at this one instant in time. Now once again we have to reconfigure the circuit appropriately at this time. So we'll go into the circuit editor again in this restricted reconfiguration mode. And we may as well take care of the switch first, because we always have to change the switch to a short or an open when reconfiguring in order to prepare the circuit for analysis, because otherwise we wouldn't know really what to do with the switch or how to handle it. So because this switch is opening at t equals 0, and we're now a little bit past that at 0 plus, that means it's effectively an open circuit. And therefore I'm just going to press the delete key here to get rid of that. Or you could use this delete button or right click, but any of those things. And now we have to treat the capacitor and the inductor here. So one of the things that's a little unusual in a second order circuit, unlike a first order circuit, is that we're going to need to know the inductor voltage. Now remember that we already kind of know its current because we found its current at 0 minus, and therefore we know that. But what we don't know is voltage, and that's going to be necessary to find the first derivative of the inductor current. So we're going to basically have to add a SOT voltage here, and I'm going to define that with passive sign convention, meaning I want to put the positive sign on the right here so that the current will point into the positive side of that voltage. And now I need to think about, well, what do I know about the inductor at this time? Well, basically I know it has 0 current. So something that always has 0 current, again, at this instant, is equivalent to an open circuit. And I can't just delete it because, again, that wouldn't allow me to keep the sought voltage there, so I'm going to change it to terminals, because basically we're changing it to a zero-valued current source, which is effectively an open circuit or a set of terminals. You're not allowed to basically put a zero value on an actual source, so that wouldn't work. Okay, so now for the capacitor, we also need to think about that. And here, once again, we're going to need its current now to find basically the first derivative of its sought voltage. We wouldn't actually really need this inductor voltage in this case, but it's safe to just put it on there, really. So I'm going to add now a sought current going up, and once again following passive sign convention, so it'll avoid unnecessary minor signs later on, and add that as a sought variable. So that's my IC of 0 plus. And now I think, well, how to simplify the capacitor itself? Well, at this one instant, I know that its voltage is still 0, which means, of course, that it's a zero-valued voltage source, or equivalently just a short circuit. So I can change this to a short circuit. Now remember, if we were in steady state, a capacitor would be an open circuit, but we're not in steady state at t equals 0 plus. That's why the result is very different. And of course, these values won't always be like this, but in this case, it is. Okay. So we've done that, and now we've completed the reconfiguration. And now we simply need to evaluate those two quantities. Well, the voltage is pretty easy because we have a short here connecting both sides of that, so that's obviously going to be 0. But the current, however, through this wire will not be 0 because of the voltage source and the resistors. So let's go in and simplify that just a little bit to make the calculation slightly easier. So we can just combine the 6 and the 1 ohm resistor in series here into a single 7 ohm resistor, and change the other one to a short, as we would normally do when combining resistors in series. So let's check that, and that is correct. And that's basically all we can do. Now you might say, well, isn't this stuff hinged by this wire? And actually it is, but the problem is that even though it's hinged, it's going to affect the current through this wire. So a wire that has a sought current really cannot be considered as making this removably hingeable, because basically, or removably hinged rather, because we still need to know this current, and if we take these elements away, then that current would be modified. So we have to keep these elements, even though the circuit is hinged. These are not removably hinged in the sense that they will affect that sought variable. So you have to pay close attention to that. Okay, so we're done basically simplifying here, all we can safely do. And now, since we have basically a single loop here, let's select single loop analysis is probably the easiest way to do this. We could also use single node pair, but I prefer probably to do this here. And we know right away that sought branch voltage, so let's just enter that, because that voltage obviously is 0 because it's connected by a short. So that voltage cannot be different than 0. So we'll set that equal to 0 and check that directly. We don't need any involved calculation for that. Okay, now we need to find this current. And there's different ways of doing it. We could write a KVL equation for this, but I could also really just kind of put it in directly here if I like. It's not 0, but I see that the 6-volt source basically is forcing current through a 7 ohm resistor, so I could just use this term here and say that I have 6 volts divided by 7 ohms, or I could even use this term if I want to compute the number right away. Doesn't matter. In fact, that might even be a little faster if you like. But you want to be careful, though, that the current is going to go from the, like water goes downhill, the current is going to go from the positive side of the source through the resistor back to the negative side. Therefore, it's going to be going opposite to IC of 0 plus, and so we need a minus sign there. So again, that's that dirty P word, the polarity that keeps creeping up if we're not careful. So we always have to watch out for that polarity. Okay, so we'll check that, and that is in fact correct. And now we can just enter the numerical value for the -6/7. The other one here is already been entered, so it's dimmed out. And we'll just divide 6 by 7 gives us -0.857. You won't, of course, have the cheat button, but I'm just doing that to save time here. Okay. So now we've completed the analysis at 0 minus, and now, or I'm sorry, that was 0 plus. And now we're going to have to consider the first derivative situation at 0 plus, because remember, we need to know not only the initial value of the capacitor voltage, but in a second-order transient described by a second-order differential equation, we need two initial conditions, not one. Therefore, we need to know Vc prime at 0 plus as well. And that can be determined basically from the capacitor current at that instant, remembering that I equals C dV dt. And so to find dV dt, we just need the current, basically. And that's why we did that analysis. So now we're going to basically use that, and we're going to take that current that we found, which was the minus 0.8571 amps. That's defined as going up. So we verified that, again, we're using passive sign convention. Otherwise, we'd have to put a minus sign in. Divide that by the capacitance, because, again, the dV dt is IC divided by C, the capacitance value. That's just from the property of a capacitor. So we divide this by 3, and computing that, that'll be minus 0.2857. Probably don't need that many digits, but it'll get rounded. Okay, so now we've finished the necessary analysis at 0 plus. And the next step is to find the Thevenin equivalent resistance seen from the combined terminals of the capacitor and the inductor. So we're going to click on Find our Thevenin. And of course, this only applies if the inductor and capacitor are either in series or parallel, but that's the type of problem that you're going to get here in Circuit Tutor. Okay, so we need to first reconfigure the circuit before we can do the calculation, as always. And now you first have to take care of that switch. Remember, switches always have to be replaced by a short or an open when we're reconfiguring. So in this case, because we're interested in the transient at t greater than 0, after the switch has become open, that's now an open circuit. So we're going to delete the switch rather than shorting it. So that's correct. And now you say, well, how do we find the resistance seen by the combined elements? Basically, what I'm going to do is I can change either one of them to a set of terminals. Doesn't matter which one. So let's just, I don't know, pick the capacitor there. And I'm going to replace that by a set of terminals, which will just get rid of the SOT voltage, which we don't need. And then the other one, I don't want that to affect the value because, of course, otherwise that would have some influence. So since I want the resistance seen by the combined inductor and capacitor, that means I basically need to delete the inductor here. So I remove that. And so and I could have, as I said, made the terminals here and then shorted this one. It doesn't matter which way you do it, but it'll be the same result either way. Now, the last thing I want to do here before exiting the circuit editor, I am allowed to kill sources in this particular mode. And so remember that when you're evaluating RTH, you do have to kill all the independent sources. So in this case, we want to turn this to 0 so that we can correctly see that resistance. So we're going to change that to a short. You could also do it after you come out of the circuit editor, going back in basically, but this saves a step. Okay, so we're now done reconfiguring. And in fact, we can really kind of see the answer here because it's very simple. And so in this case, I'm not going to bother simplifying the circuit. I can just see that our Thevenin 6 plus 1 is 7 ohms just by inspection. So I'm just going to enter that value to save a little time here instead of going into the circuit editor. Although if it's more complicated, you may or may not want to do that. You may want to go through the steps to make sure you get feedback at each step, but here that isn't necessary. Okay, so we have the RTH value now. And the last thing we need to do now is to analyze the circuit at t equals to infinity. So we'll click on that button, and that's going to relabel everything for us there to correspond to t equals infinity, as you see here. So now, once again, we have to reconfigure the circuit. So I'll click on that. And remember that at t equals infinity, because a long time has gone past and we're assuming this circuit is stable, which it is because our Thevenin is positive. And for that matter, we didn't have any dependent sources, so it has to be stable. So basically, we're going to be in steady state. Now, we'll first take care of the switch. And remember that infinity is, of course, greater than 0, so that switch is going to be open. So we delete it, as we did before. And then the capacitor, whose voltage we want, that's now, because we're in steady state, I equals C dV dt, so that, of course, is an open circuit in steady state. Okay, so at 0 minus or infinity, we're in steady state. And the inductor, likewise, is going to be a short circuit because, once again, we're in steady state. V equals L di dt, so that has 0 voltage. So it's a short circuit. And you may say, well, that's shorting out the capacitor, which is true, but that's just what the circuit does. So we have no control over that. Now, we don't kill any sources here, of course, because that's needed to find the appropriate voltage, although actually it's not going to influence it in this case. But in general, we're not allowed to kill those sources. Okay. So now, because there is a short there, this is going to be a very simple analysis. We can just do it by inspection. So I'll just do the single loop since, well, the capacitor doesn't count as part of the loop since it's an open circuit. So it's still single loop. Otherwise, I could pick mesh current. It doesn't matter. I can enter the same value no matter what I select, really. The sought branch voltage, I'm just going to enter that as being 0 because it's shorted. So again, nothing complicated needed there. And we'll check that. And that's all there is to do. So we click no more equations. And it's going to think for a minute here. So now it's summarizing everything we've done. And now we're ready to put in the final transient expression. Now, this information that says cheating information, of course, you're not going to have the benefit of that. So kind of disregard that for right now, but I'm playing as an instructor, so it gives that to me. Okay, so the only type of equation here is a second-order transient equation. And it is going to give me some very important formulas here that I will need, most definitely, in working this part. So this is our little cheat sheet, since that would be a lot to remember. And so now let's start forming the equation. We know we're going to need the capacitor voltage. That's our sought variable. It's going to equal something. And the constant voltage term would be applicable if basically that's going to be the VC of infinity value, because that's what survives to infinity. But notice that that was actually 0, so we don't need the constant term here. So all we need is one of these 3 transient terms. Remember that the simple decaying exponential is for an overdamped case. This exponential is multiplied by t, so that's actually appropriate to a critically damped case. That would be the second term in a critically damped circuit. And the third term is basically what we call an exponentially damped sinusoid, in this case specifically a cosine function with a phase shift. So which of these 3 we need depends on the amount of damping. So the first task really is to compute the damping factor, zeta, which tells us how much damping there's going to be. So again, I'm going to assume that we don't have it already computed for us and show you the algebra here that I've already worked out. So first of all, the zeta for a parallel LC, as you can see, this is parallel, requires G Thevenin over 2. And the G Thevenin is just, of course, the reciprocal of R Thevenin. So since R Thevenin we found was 7 ohms here, we just plug that in. 1/7 then is 0.1429, and the reciprocal of ohms is Siemens. So that would be our G Thevenin. And then our zeta value, the formula again is that we have to pick the appropriate one. That's G theta over 2 times the square root of L over C, which is the dual of this formula. And notice everything, if you exchange inductance and capacitance, and also resistance and conductance. So here I just plug in my G Thevenin, which is 0.1429 Siemens divided by 2 times the square root of the 8 henries divided by 3 farads. That's just based on the original element values in the circuit. And just doing that math then on a calculator, that works out to be 0.1166. And you can verify, and probably should, that is in fact dimensionless. So it has no units. Now, we observe that because this is less than 1, that means that our circuit is underdamped, which means we're going to have basically a ringing effect or a damped sinusoidal solution. So in that case, we're going to want our omega naught parameter, which is really only relevant if you're underdamped. And that's the square root of, I mean, you can use it otherwise, but it's just probably not really needed. So it's 1 over the square root of LC. So plugging in the value of L is 8 henries, C is 3 farads. I just take that 1 over that square root. And I can also check the units again, the Henry being a Weber per amp or a volt second per amp, the farad being a coulomb per volt. Volts cancel, and then amp is a coulomb per second. And then everything works out basically to be 1 over inverse second when you take the square root. So radian per second. So that numerically is 0.2041 radian per second. I'm also going to want the omega d value, and notice all these formulas are given on this sheet. I should have pointed out there's the omega naught formula. So omega d, our damped natural frequency, is, or resonant frequency, is omega naught times the square root of 1 minus zeta squared. So I've just written that here. Plug in the numbers. The omega naught we've already found is 0.2041 radians per second. 1 minus zeta squared, the zeta was 0.1166. So just computing that, it works out to be just a little bit less than omega naught because the damping is rather low. So that's 0.2027 radians per second. Now, another parameter I'm going to want here in the underdamped case would be sigma, which is zeta times omega naught. So that is, just plug in again the zeta, the 0.1166, and the omega naught, not the omega d here, but the omega naught, which is 0.2041. And then multiplying those together, that just gives us 0.02381. And this is called Neppers per second, which is, Nepper is kind of like a radian, except it's for real exponentials rather than complex exponentials. Okay, and in the final form, we're actually going to put it in, you notice here we have e to the negative t over something in seconds. So that's going to be a tau. And so this e to the negative sigma t, we're going to rewrite it basically as e to the negative t over tau. So our tau clearly is going to be 1 over sigma, since sigma is in the numerator here, in the original form. And so tau here is, and this only applies really if you're overdamped here, the 2 different taus. So we only have 1 tau in the case of the underdamped circuit. And so our tau would be right here. It's 1 over sigma. And so we just take the reciprocal of sigma, 0.02381 Neppers per second. So that works out to be about 42 seconds. And remember that the natural complex frequencies can be expressed as negative sigma plus or minus j omega d. That's kind of why that notation is introduced for the real and imaginary parts there. Okay, so we have that, and now we have to remember that the general form, as given here, would be, for the capacitor voltage, would be K1 e to the S1t plus K2 e to the S2t plus the particular solution. Remember, this is the natural or the natural or homogeneous solution. And this is the forced or particular solution. So that's the VC of infinity, which in our case was actually 0. And we know that, as shown in the introductory tutorial, using the Euler identities, the e to the S1t and e to the S2t, since S1 and S2 are going to be complex numbers in this case, those can be profitably rewritten in terms of sine and cosine. And so going through the algebra there, basically that converts into something with 2 new constants I'm calling A1 and A2 for the coefficient of cosine omega dt and for sine omega dt. And then the real part of the S, basically both of these have the same real part, which is negative sigma. So that comes out front here. And this is basically represents the e to the plus or minus j omega dt is the part that is producing the cosine and the sine. So that's how we get the damped sinusoid. So now to apply our initial conditions, we learned that VC at 0 plus was 0 volts. So we have to evaluate this expression at t equals 0. So the exponential is just e to the 0. So that, of course, is 1. So that goes away. And then sine of 0 we know is 0. So that takes away this whole term. And then cosine of 0 is, of course, 1. As you can, if you don't remember that, you can just draw a little unit circle, and remember cosine is the x-axis and sine is the y-axis. So that's a 1, and we just left with a1 there. So a1 is equal to our value that we found, which was VC of 0 plus was 0 volts in this case right here. So that means that a1 is actually 0 in this case. Now, to find a2, we need to consider a second initial condition, which is the VC prime at 0 plus. So to find that, we have to first evaluate VC prime from this general expression. Now we could go to the final expression down here, which is the single cosine, and this is basically, you can convert using a trig identity as outlined in the introductory tutorial. You can convert this down into this form. But I think this form is a little bit harder to work with in terms of finding these initial conditions, so I prefer to do it at this stage. So the VC prime, we have to basically differentiate this expression here. And remember that we have a product of two functions, an exponential and a cosine or a sine, so that means we have to, of course, use the product rule from calculus. We also have to use the chain rule when differentiating either of those functions because they have parameters in them. So basically, if we differentiate this first, that will bring down the coefficient of the t there, which is negative sigma. So we have negative sigma, and then of course get the exponential back, and then this is unchanged because we're just basically doing the v du dx, if you like. And then the second part is where we keep the exponential and differentiate this part. Doesn't matter which order, of course, we do them in since they're added. So differentiating this part, when we differentiate cosine, we get negative sine, but we also bring out the omega d by the chain rule, so we have negative omega d a1 sine omega dt, and then differentiating sine gives you plus cosine, and then we're going to bring out an omega d when you're differentiating, so you have a plus omega d a2 cosine omega dt. So we have these four terms, and now where we need to evaluate that basically is at 0 plus, and I apologize, I once again forgot my prime there. That should be a prime, which is left off on the algebra here, but that is VC prime at 0 plus, not VC. We already did VC. And basically evaluating this, when t is 0, the exponentials all become 1, and then the sine becomes 0 here, and the cosine becomes 1. So we just are left with negative sigma a1. So that's our first term, although we already found a1 at 0, so that term is actually going to go away entirely. And then from the next two terms, basically, again, the exponential is 1 because it's e to the 0, and then the sine will again be 0, and the cosine will be 1. So that just leaves us with a simple omega d a2, and that is equal to the value we computed from the circuit analysis for this, for the VC prime. Remember, we got that by taking the capacitor current at that instant divided by the capacitance, which we've already done. And so that was minus 0.2857 volts per second. That was one of the things we entered at 0 plus, or the first derivative really. And so we divide here by omega d, which we've already calculated, which is up here, the 0.2027. Again, don't confuse that with omega naught, which is a little bit different value. So dividing there, the seconds cancel out, and I just get volts. So that's minus 1.409 volts. That's our A2 value. Now, we don't have the option to enter A1 and A2 type form here. They want us to put it in a simplified form. So we're going to basically use this form now, which is the A e to the negative sigma t cosine of omega dt minus phi, and then plus the particular term, which, although in this problem, this is 0, so we don't have to worry about that. So to find A, we use the formula that's given to us here, which is the square root of A1 squared plus A2 squared. Basically follows from using the trig identity to get from this stage here down to this stage. And so since A1 is 0, that's quite easy. We're just taking the square root of A2 squared, and so that just gives us the absolute value of A2, which is 1.409. Notice, however, it is positive, whereas A2 itself was negative. And then to find the phase angle, we basically, because the A1 is not negative, we can just use the so-called atan2 function. Basically, it just becomes the arctangent of big A2 divided by big A1, and that is going to be the arctangent, or inverse tangent, of negative 1.49 divided by 0, which is, of course, negative infinity. And if you remember on the unit circle, that would be minus 90 degrees. That's where the cosine goes to 0, but the sine goes to minus 1, and therefore the ratio gives you negative infinity. So that's minus 90 as our angle. And so now we have all the parameters we need to enter, and we know that we need now the underdamped term, which is this term here. So click on that. And the unit, well, let's do that first, because we know the unit here, it has to be amp, volt, or watt. So we're going to just type the volt to replace that, so we have a correct unit. Then the A value here, this is going to be the A value, which is the prefactor, based on this formula here. And so that prefactor said was 1.409, so we enter that. And then the e to the negative tau, that's this part here. So the tau, remember we computed up a little higher, was 42 seconds. That's the reciprocal of the sigma parameter. So that's going to be just 42. And remember the thing that multiplies t in the cosine is omega d, all right, as you see from this formula here. And so our omega d, we had evaluated that earlier as being 0.2027. So we'll put that in. Remember, that's not omega naught, it's omega d, which is a little bit different. And then the phase angle, again, was minus 90. So since there's a minus there, it's minus the phase angle, so we do have to put that in with its sign, minus 90, and then that'll get added effectively. Okay, so we put all the parameters in, we check that. That is in fact correct. And now we have the final expression here, which we've entered. And basically now we're done. We just click no more equations. And again, you could go back if you're unclear on any of these steps. You could pick those steps to show. I'm going to skip that right now, and we are done.